Check, 1, 2. Hey everyone, good afternoon, and thank you so much for attending this talk. My name is Sohan Maheshwar. I'm a cloud advocate. I've spent 6 years at Amazon and AWS, and I spent some time at a startup called Fermion as well, where I worked with WebAssembly. First, big thank you to the organizers of this conference. So yesterday, they took us to the Jungfrau Joch for an outing, and it was quite ironic that it was a super cloudy day, given that today is Cloud Native Day. But one of the speakers actually told us about how at the Jungfrau, at the bottom, there is hardly any snow nowadays because of climate change. And unfortunately, climate change is very real and is upon us. And tech really is at the heart of everything that we do, right? Everything in our lives is impacted and influenced by technology. So given that we work in tech and we have some influence in this ecosystem, I think it's very important to talk about sustainability in tech. And there are some estimates that actually say that the IT ecosystem has as much carbon emissions as that of the airline industry, right? And if you think about it, it's actually quite mind-boggling. And given the advancements of everything that we do with AI and blockchain and just in the cloud, I think it's super important to start talking about sustainability in the cloud. So today, I'm going to look at sustainability in the cloud via the lens of serverless computing and specifically with WebAssembly. And I'll try and take like a unbiased opinion or unbiased view, rather, of this particular topic. Now, I have a question for you, which is all of us probably work in the cloud. And all of us probably have things like daily stand-ups, weekly scrums, monthly reports. But how many of those actually include any metrics about sustainability? And my guess is not too many. Right? And there's a famous saying that goes, if you can't measure something, you can't really improve it. So essentially, the Green Software Foundation, which looks to put a lot of standards in sustainability in tech, has come up with a formula to sort of look at a metric to look at carbon emissions. So that formula is the software carbon intensity, which is equal to C per R. So let's dive deep. Right? So essentially, C stands for carbon. It's your carbon emissions. And R stands for the rate of something. So this is not an absolute value. So you don't get 10,000. Right? It is per something that you do in the cloud. That per something could be per API call. It could be per machine learning model training run. So you get to calculate C per something that you do in the cloud. So let's break this down even more. The C could be expanded to two things, O plus M. So let's look at M first. M is essentially the embodied emissions of the hardware needed to make a software system. So if a piece of your code is running in the cloud, it's running in a piece of hardware in a data center somewhere. For that data center to be powered, there has a lot of carbon emission that has gone in for that to happen. Right? The chips have to be created, the memory has to be created, things have to be transported to that data center, there's water cooling, all of that is part of the embodied emissions. O is the operational emission, which basically is equal to what your software takes in that piece of shared hardware. So that could be the energy consumed by the software system into the location-based carbon intensity. What this means is different locations in the world have different ways that they can get these metrics. Right? So an area in Europe, for instance, may be more greener than an area in, say, Asia. I'm just taking two examples. So that is the location-based intensity. Now, this gives you SCI, or software carbon intensity. And the Green Software Foundation goes further and says there are 3 actions that any of us working in technology can take to reduce this SCI value. So whether you're a programmer, tester, architect, we all can do something to reduce this SCI value in our spheres of influence. The first one is energy efficiency. Right? How do you use less electricity to perform the same function that you're typically doing? Second is hardware efficiency, which is using fewer physical resources to perform that same function. And the third is just being carbon aware. Like I said, different regions have different ways that they get their electricity. So for instance, say you have a workload that's running in the cloud that you can actually shift to a different region that is greener. You are already reducing your SCI right there. Now, for today's talk, I want you to think of everything that I speak about after the slide in terms of being either more energy efficient or hardware efficient. And of course, we are going to be talking about sustainability, but invariably, the things I will speak about also uh, result in a reduction in cost as well. That those two things pretty much go hand in hand. So basically, should I just write everything to be super efficient and fast? Well, ideally, yes. But the real world and it doesn't work like that. We all have these complex projects that huge teams and a large number of people really work on. So how do you go about that? A few people would have seen this particular slide or this particular image all over LinkedIn. It goes viral every once in 6 months, I think, when people feel like talking about sustainability. It's from a paper that was written a few years ago, right, where they took different languages, everything from low-level languages like C, C++, and Rust, to the more modern programming languages like Python and Perl. And essentially, this study looked at energy consumption, at time, and memory as well. So they took the most either efficient energy-wise and placed it at 1, and everything else is relative to that. And the trend you see here is all of the low-level programming languages like C, Rust, C++ tend to be at the top, whereas the more interpreted ones like Python and JavaScript and Ruby tend to be at the bottom. Now again, this doesn't tell the full story, because realistically, we already have projects that are written in some of these languages. Secondly, you want to use, say, Python for something in the data science field. So it's not a realistic thing to convert everything to C code and just be like, cool, we have lesser SCI. So that really isn't the full story. The other part of it is once we're having these applications in the cloud, what happens is very few applications rarely use all of the CPU all of the time. In fact, if your application was doing that, it is actually being energy efficient in a way. Because what is counterintuitive is even when a CPU is idle, it's still conserving or still consuming energy. Right? So if you look at this paper, they actually say that at 30 to 60% of maximum power when utilized at 10 or lower capacity. So the power that's being used in this case is about 100 watts, even at like a very low utilization. So basically what this means is if you can utilize a server better and use it to its maximum capacity, you are actually extracting a lot of value out of it. Second part of the story, this is from Datadog's State of the Cloud report from a couple of months ago, is containers specifically are especially guilty of this. Right? More than 80% of container spend is wasted on idling resources. For those who have actually worked on containers, I think you will identify with this slide a lot. And I think what tends to happen when we design for capacity is that we design for peak capacities. We're like, OK, at that one time in the year, our usage is going to be so high, so this is what we are designing for, whereas your typical average daily consumption is much lower. Right? And because of which, so much of your container is just sitting idle, consuming resources. And if you think about it, and these last two sides, they're not energy efficient, they're not hardware efficient, right? So that's a lot of C over not a lot of R. You're using so much carbon and for nothing. If you look at the evolution of compute and compute in the cloud, we started with the bare metal days, and then we moved to virtualization, using someone else's computer, like with EC2, where thanks to hypervisor, you could scale infinitely in the cloud. We moved to the days of containers, and now all the talk is of the next paradigm shift. A lot of people say serverless is that shift where, as a programmer, I don't have to worry about scaling up and scaling down. I just write my code. Just to context set, there are different ways of thinking of serverless. One is a type of application, something that is completely event-driven. So say you have an application to resize a photo. You're not running it on EC2 constantly waiting for that one person to resize photos, right? When someone wants to do that, they will send an event, it will process that event, and then you send a result back. It's basically stateless, so it doesn't capture any state. It's ephemeral, so it runs only that one particular function that it's intended for. The other way of thinking of serverless is it's a development model. It's a way for us to build applications where I, as a developer, or you, as a developer, you only focus on writing business logic. You're not focusing on scaling servers up and down. You're not focusing on writing server daemon processes. And your platform's taking care of most of the things, like config, key value, etc. And lastly, you can think of it as a function as a service. You have a function that does one thing and does that thing really well. You can have that as a service, either internally or externally. Right? So that is the idea of serverless. Now, serverless has gotten very popular in the last few years. You will have advocates really talking about how they've saved on costs and all of that with serverless. And some of the reasons I think are very strong. I'm a big fan of serverless. One, like I mentioned, full focus on business logic. You can scale up and down without having to think about it. But the last two, I think, are the key ones, which is increased density and better utilization of the hardware, which are both cost savings and energy savings. When we say increased density, basically you can have more functions in a piece of hardware, and thereby you're utilizing that hardware better. The key to understanding the concept of serverless and density and utilization is to understand this concept of multi-tenancy, right? Having many tenants in one piece of hardware. I would highly recommend reading this blog, brooker.co.za. Mark Brooker is one of the original engineers of Amazon EC2 who still works in Amazon working on Lambda and the serverless offering. Very interesting blog. We'll give you a deep dive into it. I'll give you a sort of summary, right? Essentially, what they say is that multi-tenancy, think of it as a cramped apartment where you have on one area of land, you have many houses which are sort of sharing some resources, right? And it's a very rudimentary analogy, but that's the idea of multi-tenancy. When each of these tenants can sort of run independently of each other without affecting one another on purpose or accidentally, you are getting better utilization of that hardware. And the value of a system is essentially the long-term average traffic that that system gets. Yeah? So let's take a visual look into how this sort of looks like. So this is a graph that charts time and resource consumption, and we have two functions running on a piece of hardware. So these colorful lines that you see at the bottom, they are function A and function B. Now, with two tenants on this piece of hardware, our average resource consumption was 10. But these resources sometimes had peaks, so your peaks was at about 17, I would guess, right? The top line there. And the difference between your peak and your average is about 1.7. That's the ratio. To get the most out of a piece of hardware, you need to bring this gap as close to as possible. Increased density, again, energy and cost efficient. Just by adding two more resources, right? So we have resource A and resource B, but we added two more resources. Sure, the peak went up, right? The peak goes up to 23, I think. But look at the average. The average is about 19, but the ratio has reduced to 1.25. Right? It's reduced from 1.7 to 1.25, just by adding two more tenants to that same piece of hardware. So this really is the key to understanding why serverless is potentially or is more sustainable and can reduce your costs and energies, because you can have more tenants in a particular piece of hardware. And essentially with every wave of cloud compute, we are getting better and better multi-tenancy and better utilization. If EC2 and virtual machines look like this, where you could run a few apps on one piece of machine, and containers may be expanded on that, you can have really dense functions in a piece of hardware in serverless. So that really brings about the energy and cost savings that we were speaking about. Now, here's the thing. Everyone does serverless with the three big hyperscalers, typically, with AWS Lambda, Azure Functions, Google Functions. But how serverless is centered or is built on the hyperscalers, there's one big problem, and which is the problem of cold starts. Right? A reason why a lot of people do not use serverless in production where you need low latency is because of this problem of a cold start. What's a cold start? Well, let me explain. Essentially, you have a function running in the cloud. It's essentially reused from your EC2 utilization. It's something called a firecracker virtual machine. Right? So when it receives an event, it needs to start up. And there is a very finite time between 250 and 500 milliseconds for that function to start before it can actually process something. Now, this delay sometimes is not what people want in the cloud. So what they actually do is they keep that instance warm by sending periodic pings to that function to keep it warm so that the cold start time reduces. And that time is actually borne, or that cost is borne by you as a developer, you as someone using a cloud. So then serverless starts actually becoming a little expensive. At the same time, even if you look at the AWS docs, they mention that cold starts typically occur in under 1% of invocation, and it could be from anywhere under 100 milliseconds to over a second. And for lots of applications, having 1 second latency for a function to start is not part of the requirements. At the same time, people have tried like a serverless model with containers as well, if you've used AWS Fargate. Azure functions are invoked once per minute or less. And if you read this paper from 2020, it states that the cost of keeping these applications warm so that there is no cold start is a little expensive. It makes it a little expensive for people actually building in. And yeah, you might have seen posts online about how serverless costs have risen in the past. So here is where WebAssembly could potentially make a big difference in making sure that serverless actually works in the way or in the vision that it was intended. And I will share some benchmarks that we had done some time ago to actually compare Firecracker and WebAssembly. Anyone here has used WebAssembly either on the server side or anywhere? Few of y'all, okay. Let me context set for everyone here. Essentially, WebAssembly is a simple bytecode format, right? It's a simple bytecode format. That's all it is. And what it was is it was designed as a portable compilation target. So you could create a WebAssembly file, and you could run that on AMD, Intel, ARM, or Linux, Mac, Windows, Raspberry Pi, wherever, right? It could work anywhere. And the idea was that you could write code in any language, convert that to WebAssembly, which could then run anywhere. All it needed was a WebAssembly runtime. And if you're thinking, hey, this kind of sounds like a JVM, well, you're not too far from the truth. It's just that WebAssembly is not owned by anyone. It's a standard, so it's a technology that anyone can actually use. And if I say WASM, it's just short for WebAssembly. Now, WebAssembly was developed in, I think, sometime in the 2010s by a bunch of the browser companies, because they were like, hey, what if we could put Python or Rust code and run it in the browser, right? And companies like Adobe, Shopify, Figma still use WebAssembly because it is so performant, it's cross-compilation, portable, and so on. So these features of WebAssembly, and this is how it works, where you write code in any of these languages, it converts it to that instruction format, and that could run on the edge somewhere, on edge devices like IoT, running Linux. It could run on your local machine or ARM64. It could run on a VM running x64 as well. The thing is, all of these features of WebAssembly were really good for the browser, but people like, hold on, this actually makes sense if you also can run it on the side of a server. But for something to run on the side of a server, you need access to things like system clocks, networking, kernels, and files, and so on, which didn't exist. So towards the end of the decade, so around 2018-19, a new system was introduced called WASI, or WebAssembly Systems Interface, which took all of those good parts of WebAssembly and extended it so that you had access to files, networking, system clocks, and so on. TLDR, you could run WebAssembly outside of the browser. You didn't need a SpiderMonkey or one of those engines. You could actually run it outside of the browser. And WebAssembly was designed to be security sandboxed by default. So nothing can access a WebAssembly module, including an API, a file. That module can't access anything outside as well unless you give it permissions. So by default, security sandbox, again, great for servers. Just to give you some numbers again, right? I mentioned it is very portable in the sense you can swap out underlying architectures and put it along. WebAssembly was designed to be very, very lightweight, right? It has a reduced instruction set, uses shared memory. So a simple Hello World WebAssembly app, which I will show you, the OCI artifact is about 284 KB, right? So it is that small. Again, very good when you think about cost and energy savings. It's sandboxed by default, as I mentioned. And because of those things, the startup times of a WebAssembly app is under 1 millisecond, thereby solving the cold start problem that I spoke about. So in the original paper for Firecracker, again, worth a read, mentioned down below, the team that came up with Firecracker essentially listed out listed out 6 characteristics of an ideal serverless unit. Right? So this was the team that built Firecracker, which is the base for Lambda. They mentioned you should have isolation. Right? Like I mentioned, one serverless function can't interact or shouldn't interact or affect another serverless function, so have isolation. You need overhead and density. You need to be able to run thousands of functions on one machine with very good utilization. Performance, you need consistent and near-native performance. That's the holy grail. That's what we always want. You need fast switching. Because these things are so ephemeral, you need to be able to quick start something, perform something, and then clean it up for the next function to do something else. You need to be able to overcommit resources. And this part is very interesting. Because sometimes, say, one app in your serverless stack gets a spike, what are the odds that the other apps also don't get a spike? Right? So serverless essentially relies a lot on probability and statistically for one function not to be related to the other. The more diverse and the more unrelated those functions are, this soft allocation can actually happen. Right? So there is a lot of modeling that goes into that to sort of figure out how to add these. And lastly, of course, most important for us as programmers and devs, you need to be able to use your favorite libraries, your favorite hosts, and so on. Because if there's no compatibility, then it makes it difficult. So here's a comparison between Firecracker, the micro VM, and WebAssembly itself. In terms of isolation, the Firecracker micro VM is sandboxed. So the equal and WebAssembly is security sandboxed by default. So I think they'd be equal. Here's one place where WebAssembly really shines in terms of overhead and density. To get about thousands per node, you needed a 48-core, 382 GB RAM with a 3360 GB disk, whereas you could do the same thing with just 8 cores, 32 GB RAM, and a 100 GB disk, right? Because we said that WebAssembly is designed to be lightweight and performant. In terms of performance, you can get near-native performance in both. In terms of fast switching, like we said, WebAssembly can have under 1 millisecond start to cleanup time. With micro VMs, you see about 125 milliseconds. That could go up to about 1 second as well. In terms of soft allocation, micro VMs and Lambda especially performs amazingly well. It's in production in the biggest enterprises in the world. So you can run in production with like oversubscription up to 10x. Whereas WebAssembly is, well, we don't know. It's untested. It's new. So hopefully in a year or two, we'll get some data to see if it actually performs as well. And in terms of compatibility, micro VMs are compatible Linux and KVM only. Whereas for WebAssembly, the underlying OS and platform architectures are agnostic. It was designed to be so much. Only supports libraries that can compile to WebAssembly, though. Right? So that is a hard requirement. I'm guessing some of you all prefer seeing some code as to how WebAssembly looks. So I will show you a quick Hello World demo. again, very simple, like 2-minute demo of how to write a WebAssembly app. And I'll be using an open source product called Spin. Essentially, Spin is a developer tool for building WebAssembly apps. It's completely open source, so feel free to also contribute. And yeah, I'll just show you Spin. I think it's just easier to show you code that way. I've already installed the SDK, so I'm just going to say Spin new. And what you'll see here, and hopefully you can see it at the back, on the left, you will see HTTP and Redis, among other things. Those are the events that can trigger a particular function that's running in the cloud, right? We said it is event-driven. So the most common, of course, is HTTP. So you have an HTTP event which triggers a serverless function. On the right, you'll see a bunch of languages from Rust to TypeScript to Python. That is the advantage of WebAssembly, right? You can write code in any of these languages and convert it to WebAssembly. I've heard all the cool kids are doing Rust, so I will do Rust as well. And I'll just call it Swiss Cloud, maybe. Description. So you'll see something called a HTTP path. The default is just the default, but you can specify a path that will trigger this particular application. Right? So if I can say /checkout will trigger this, it will trigger this. Again, the beauty is in the same app, I can write one function to be in Rust. So /checkout triggers a Rust function, but /by triggers out a Python function. They both compile to WebAssembly, so it would work in the same code base. Right? So I'll just leave it as is, and that's it. Right? So I will do Swiss Cloud. The code itself is fairly straightforward. If you've used Azure Functions or Lambda, this should be, this should be pretty straightforward to you. Let me just, yeah. As you can see, at line 6, essentially it's a function. It's a simple request-response model. So there's a request coming in that we can print out. And you can do, typically you would do something here. You would process an event. You would resize an image, do some math, whatever, and then you would send a response back. So I'm just going to say hello cloud day. And yeah, I can just build this app using the CLI. I'll just say spin build. Oh, I did not go, yeah. Spin build. And yeah, it essentially fetches the crates since it's the first time, but after that it bypasses this step as well. It takes about a couple of seconds. And the developer experience of this SDK is quite cool because I can actually have a local test running, up and running. So on localhost, it's created this function for me to test out. So I will just do a curl function to localhost, and I can see that hello cloud day up and running. Right? So let me stop this. I'll show you the WebAssembly app itself, and that will be here, I think. Yeah. So this is the WebAssembly app that's been created. As you can see, it's a pretty small app, about 1.9 MB. And that is your HTTP server API, right? A small Rust app that's converted to WebAssembly, about 1.9 MB. If I do this, yeah, that's WebAssembly. I don't think any of us can read that. But essentially, this is what it looks like, right? So yeah. So that was a very, very quick demo of Spin. For the folks who do a lot of Kubernetes and your stack already includes Kubernetes, at KubeCon this year in Paris, if you saw the keynote, there was a launch of this different open source project called SpinCube. So it was a collaboration between Microsoft, SUSE, Liquid Reply, and Fermion, where you can put WebAssembly apps into your Kubernetes cluster. Right? And this results in very dense Kubernetes clusters, far more efficient energy and cost-wise than a traditional Kubernetes cluster. So if this is something that interests you, check it out. Now, this might sound, all of it might be like, whoa, this sounds too good to be true. Why isn't everyone just doing Wasm right now? Well, one is it is fairly new, right? It is something that's fairly new, and it's still in a state of evolution. In my opinion, there are 3 things that I think would make this adoption a lot more. Right? So one is the language ecosystem needs to evolve a little more. When it comes to the lower level programming languages like C and Rust, the support for WebAssembly is, again, in my opinion, pretty good. There are some tool chains that convert code into WebAssembly. So you will have like a fair set of features, right? But unfortunately, we end up writing a lot of code on things like Python and JavaScript, which are interpreted languages. Now, that is a little more difficult, and the support for those interpreted languages are still in a state of evolution, depending on the language. So in Python, for instance, there is no official support for things like NumPy and Pandas. There are some community-created ones which convert that into Wasm, and then you write code in Wasm, and those are like just-in-time sort of snapshotted to create a WebAssembly app. But say there's a new library in Python that everyone's using, well, it will take some time for that to be converted to Wasm, right? So that's there. And unfortunately, a lot of enterprises still use Java, which is, I doubt they'll have support for WebAssembly. I think with Kotlin and Scala, there are some, again, like community created some support, but it's not great. .NET, though, looks promising. I think .NET 8 was the one that was launched recently, and there is some sort of support for WebAssembly, but you get the idea. The language ecosystem needs to evolve a little bit. The second problem, because of this, there is no like widespread big adoption just yet, and rightfully so. To adopt anything new, you need to see it be successful at scale with the company for like case studies, learning, etc. It's at a stage where everyone's trying to look at the other to be like, let's wait for that. So there's that. And right now, there's no widely used package registries yet. There are a few registries in development. There's something called WARG, or WebAssembly Registry something. And there's also wa.dev, another WebAssembly registry for components and packages. But again, nothing that's been widely adopted by the industry. So some of these steps in the developer experience still have some way to go, right? Which is why if this talk has been interesting and you're like, wow, I'm going to change everything in my enterprise to WebAssembly today, I'd say it's, look at maybe starting off with proof of concepts or greenfield projects, and you can reduce your costs and be a little more energy efficient using WebAssembly. Now, this is a snapshot of what today looks like in the Wasm world. I just want to give you a sneak peek of what the future could look like with WebAssembly, serverless, and cloud computing, right? And there's something actually very interesting in the WebAssembly world, which is live right now, and it's called the component model. So right now, say you have a JavaScript app, and you're like, hey, in this app, I need to parse YAML, and I need to format dates. And you're like, oh, I can't find a good one. So then people end up rewriting a YAML parser in JavaScript and a date formatter in JavaScript. It turns out Python's really good with dates and numbers. You could write a Rust YAML parser for performance, but this wouldn't work in a traditional coding environment or in an app. But in WebAssembly and with the component model, you could actually do this, and you can do this right now. So in one app, you can have code that was originally written in Python and code that was originally written in Rust sort of working together, right? Each of these would be individual components, very lightweight components that could eventually be on registries that people could use. Again, visually, if you want to look at it, say you have component A written in a certain language. Component A basically says, hey, I'm going to export this functionality. Component B can be like, hey, that's exactly the functionality I need. And both component A and B could be in completely different programming languages in what they've written. Because they're being converted to this binary bytecode format called WebAssembly, you could have a new component called component C, which actually does something, right? And this opens up a lot. It opens up lots of different possibilities of how we think about code itself. I'm just going to give you a small example, again, through the lens of being more energy and cost efficient. If you look at CI/CD today, continuous integration, continuous deployment, this is sort of what it looks like, right? And I've taken two, like just straight out of GitHub, just two random files. So this is a tool called Goth. It's a Go tool, and it's a CI YAML file, right? And if you look at line 5, there are all these Go versions that are bundled. There are all these operating systems that are bundled. So your build file typically has stuff for operating systems, architectures, language versions. Your test file has the same thing, and then what you deploy as your package has the same thing. Same example, this is straight out of the Docker documentation. Again, look at the top, right? Platform, you're building for different platforms and so on. Now, this could be more energy and cost efficient. So with the component model, you could unlock a very different way of looking at CI/CD in the future. You can go from that to just one build where you have the WASI preview to, WASI, as I mentioned, WebAssembly Systems Interface, standard build written by the Bytecode Alliance, which is like CNCF, but for WebAssembly. For your test, you just have one WebAssembly runtime, which has been tested, which you know can run across architectures and platform, and your components are already packaged, so you don't really need to repackage it again, right? So I don't even need to give you numbers as to how much more efficient this would be, when it actually gets mainstream adoption. So do check it out. Some things for you to look up next. The component model, I think, is very exciting. It's very new. WASI Preview 2, which was the basis of the component model, was released earlier this year. So do check it out. If you would like to build serverless WebAssembly apps, Spin is a great open source tool to do so. And in general, if you want to read up about sustainability, I think the Green Software Foundation is a good place to start. Anyway, hope you learned something new today. Feel free to connect with me on LinkedIn. I'm around as well. We have, I think, 5 minutes for questions too. So thank you.
Thanks so much, Sohan. Are there any questions for Sohan? Back there. This time I won't throw it.
Thanks for the presentation, first of all. You briefly touched the subject, but I'm not sure I really understand, so I'll ask the question. It's about package dependencies. Like you mentioned, for example, Python. What if my application needs to use like some really specific Python dependency, like whatever, like geospatial data manipulation, and that is not part of the WebAssembly runtime? Yeah, how do you deal with those package dependencies?
Yeah, you articulated very well why one of the reasons it's not getting mainstream adoption. There's not too much you can do right now if you want all of that as, like, say, a WebAssembly app, right? Like, for instance, someone's like, I want pandas in my app. And say, let's assume there's no support for it. There's no way for you to get that into like a WebAssembly app. What happens in real-world scenarios, especially enterprises, is invariably there's a library of framework that's internal that only that company or like a small bunch of companies use, which doesn't have like a WebAssembly equivalent, and then people actually struggle to get that project to completion. So yeah.
Thank you.
I will say though, based on that, sorry, I just train of thought. A new thing called componentized Py and componentized JS is out in the industry, right? So these are different ways of looking at interpreted languages in WebAssembly, where they look at it from this component model type of view. So this makes it a little easier for adding frameworks such as this, like a very specific thing, into WebAssembly later on. Right? I don't want to go into like the details right now because we don't have time, but essentially there's a concept of a world in WebAssembly and components. And any different WebAssembly component in that world can talk to other components. So yeah, essentially with componentized Py and componentized JS, the ecosystem has gotten a little better for supporting such frameworks, right? So that's the evolution that it's going through. Yeah.
Thank you.
Up here in the front. Thank you.
You made the example with Rust. If you do the same example with Python, do you get any worse numbers in size and speed, or is it the same?
Okay, so I hope everyone heard the questions about, I showed the numbers in Rust, do you get the same with Python? In terms of performance, yes. In terms of size, the size is slightly bigger, right? Because like I said, a lot of the Python libraries have to be converted to Wasm, and they're bundled with the Wasm app. So it's not as low as the Rust file, because Rust, you don't have to do that. But with Python and JavaScript, the file size is a little bigger. Yeah.
More questions? Over here.
What about the runtime? Is there something to look for, or are there any differences?
Yeah, so there are a few runtimes in the industry right now. The industry standard is Wasm time. So all of the big companies like Microsoft and Fastly and Fermyon and Cloudflare that are working on WebAssembly are part of this consortium called Bytecode Alliance, right? And they support the Wasm time runtime. There are a few competing runtimes as well. In terms of my opinion, at least, I think Wasm time is like the industry standard, so I would suggest using that for any WebAssembly project. But the idea behind a runtime is that that runtime is tested to run across all these architectures, platforms, OSs, etc. And any WebAssembly app should be theoretically compatible with the runtime, right? So, yeah.
We have time for more questions.
You mentioned at the very beginning that these functions as a service work very well when you have stateless problems. You also mentioned machine learning. In machine learning, you very often have stateful. And how does that compute? Do you think that this is going to work out, this fast approach, also for machine learning applications and stateful applications, or do you think this is rather for other applications?
So for things like inferencing in machine learning and training, I think that's a very different problem. In fact, Fermyon had created a serverless AI product, which still exists, which sort of works under like a similar thing where essentially they took the Llama 2 language model and they had it running in like an A100, or is it A1000 or A100, the NVIDIA running in the cloud. And they built some sort of, I'm not sure about this part, how it was actually optimized, but some sort of WebAssembly optimization around it, which you could access via their SDK, which was like an internal API, right? So I think for that part, it might help, but I'm not entirely sure if it would help for things like inferencing later on, right? Or model training and things like that. I'm not sure how that would work, yeah.
Thank you. Last question.
I have a question about observability. So you have spinning up like thousands of those functions. What do you think the future will bring? Will like Wasm integrate into Kubernetes ecosystem, or will come up with their own one?
Yeah, no, that's a good question. So as of KubeCon in Paris last year, SpinCube was launched, where you can put like these spin apps into a Kubernetes cluster. From initial benchmarks, it looks very promising because you can have really fast and dense Kubernetes clusters and reduce on your utilization, so you're saving on cost and energy. And there's support for OTel, or Open Telemetry, in Spin right now. So you can get observability into each of those Spin functions that are running in your Kubernetes cluster as well. Yeah. And I think Spin's OTel support was launched like very recently. I just saw like a blog post about it. So I don't know in what state of like maturity it is, but there is support for sure.